Hi, Mathies. This is the last unit, proportional reasoning. This is the first lesson, so comparing and interpreting rates. This unit's a bit of a hodgepodge, but again, it's all talking about proportions and items in relation to one another. So we'll see quite a few different topics, and some of this is actually pretty important when we get to 30-2 if you are planning on taking it. So let's minimize that. So comparing and interpreting rates. So today and tomorrow, or today and the next day, we're going to talk about rates a couple of times. So a rate is a comparison of two measurements or amounts that are measured in different units. So some examples of rates are something like speed. So speed is a rate, and what it is a comparison of is something like kilometers per hour. So it's comparing two different things. It's comparing a distance in kilometers and hours in minutes. So it's saying how many kilometers can you travel per 1 hour? Pricing is another big one. So something like gasoline for your vehicle is priced as dollars per liter. So it's relating to different things, a money and a volume. Something like how fast you can type is in something like words per minute. So again, two different measurements or amounts, this should say or, I know it looks like it says of, that are measured in different units. So in order to compare rate, we write them as unit rates in which the second terms are equal to 1. So it's always like kilometers per 1 hour and pricing per 1 liter and number of words per 1 minute. That's called our unit rate. So sometimes you have to do some unit conversions based on the information you're given. So in the first little example here, it says Carol can text at a rate of 65 words per minute, which is pretty fast. Jed can text at 290 words in 5 minutes. So Carol's here is a unit rate because it's saying the number of words per 1 minute. So 65 words per 1 minute. Whereas Jed's, we're given a little bit of different information. So Jed can do 290 words in 5 minutes. So if we take 290 and divide it by 5, we get our unit rate for Jed, which would be 58 words per 1 minute. So we're dividing that 290 divided by 5 to get us our unit rate, or our unit, or our number of words per minute. So here, Carol is faster, right? She can type 65 words, whereas Jed can only type 58 in 1 minute. So that's kind of talking about unit rates. So the next one, so this is just an example of a currency table. I'm not sure what year it's from. And so these are a little bit confusing to kind of read through because there's quite a bit of information within it. So we have a couple different currencies that we have. So US dollar, the euro, the Great Britain pound. I think this must be the Indian rupee, the Australian dollar, and the Canadian dollar. And it's talking about their value of one versus the other. So how you kind of read this, we might ignore this inverse part for now. So we'll just look at the first column. So 1 US dollar is equal to 1 US dollar. That should make sense. 1 euro is equal to 1 euro. But then we have a little bit of our conversion factors within this. Let's see if it'll let me erase. So 1 US dollar is equal to 0.74537 euros. So that's saying for every $1, we get 0.74 of a euro. At this time, whatever time this was, 1 US dollar was equal to 1.01676 Canadian dollars. So that's how we actually read the table. What this inverse part is that I kind of crossed out for now is talking about 1 Canadian dollar would be equal to 0.98 of a US dollar. That's what that inverse part is equal to. It helps sometimes with conversions, but you can just use the top row typically. Sorry, we don't have a lot of room here. So this is saying $80 Canadian into US dollars. So when you travel to the States, you have to get US dollars, and when you come back, you've got to convert it all back to Canadian, unless you're like me and you just save your US dollars in a little jar and then you use that next time you go. So if we had $80 Canadian, and we wanted to figure out how much is that in US dollars, we need to use this table. So we're dealing with US dollars and we want to get it to Canadian dollars. So the conversion factor that we're going to actually use here is 1.01676 Canadian dollars is equal to 1 US dollar. So this is kind of like unit conversion that you would have used in Science 10 potentially. So $80 Canadian, we know that 1 US dollar is equal to that 1.01676 Canadian dollars. So the reason that I kind of wrote it like that is because then I can kind of see that Canadian dollars on the top, Canadian dollars on the bottom, so those units are going to cancel, and I'll be left with US dollars on the top. So now, as far as the calculator strokes, anything on the top is multiply, anything on the bottom is divide. So I'm going to go 80 multiplied by 1, still 80, and then from there I would divide that by that 1.01676, and so 80 Canadian dollars is actually equal to 78.68 US dollars. So we needed to use that conversion table in order to figure out the value of 80 Canadian dollars. And again, just thinking about, does that logically make sense? We said $1, 1 US dollar, sorry, is equal to slightly more in Canadian dollars. So in this case, 80, it should be a number smaller than 80, but not very much, right? This 1.01 is not a big number. Sorry, I'm just going to pause for a sec. And we're back. So the next one that it's asking us about is $150 Australian dollars, so AUD is Australian dollars, into Canadian dollars. So the tricky part with this one is the fact that we don't have something right now that will directly relate them. So what we need to do is convert from Australian dollars to either American dollars, the euro, or the Great Britain pound. It shouldn't matter at all which one we do, as long as we then use that US dollar, euro, or Great Britain pound to convert it into Canadian dollars. So if you were in front of me, I would then say, which one do you want to convert it to? And you would yell your answer and we'd all be excited. But you're not here, so I'm just going to make the executive decision and I'm just going to use the US dollar one again. So you can try this out and try it with the euro and try it with the Great Britain pound, and you should get to the same answer. There shouldn't be any difference. So first we need to convert from AUD to the US dollar. So 1 US dollar is equal to, oh, I have it underlined right here, 0.97698 Australian dollars. So now I will be converting from Australian dollars into US dollars. So 150 multiplied by 1 divided by 0.97698 gets me a total of 153.534, I think there's more digits than that, US dollars. I'm not going to round this quite yet because I still need to do one more conversion. So I haven't gotten all the way, I've only done Australian dollars to US dollars. Now I need to take that $153 and convert it into Canadian dollars. So 153.534 US dollars multiplied by that conversion factor for US dollars to Canadian dollars, which is this one that is rectangled up there. So again, 1 US dollar is equal to 1.01676 Canadian dollars. So 153.534 US dollars is equal to, I'm just going to round it now to dollars and cents because that's what makes sense in terms of a money question. So 150 Australian dollars is equal to 156.11 Canadian dollars. So that's what exchange rates actually are. These numbers are pretty crazy actually. Like this chart is pretty wild. I can't think exactly what it's at now, but the Canadian dollar is not more valuable than the US dollar. I think we're probably somewhere mid 70s, maybe low 80s. Haven't checked in who knows how long since the old COVID. So this chart is pretty wild, but you can see how to use it at least. So slopes and rates. So slope was a big thing in Math 10C that you would have looked at, and probably in any physics course that you've looked at before as well, so even Science 10 physics. So in a graph of the relationship between two quantities, the slope of a line segment, so slope is kind of saying how steep is the line, represents the average rate of change for these quantities. So this is your formula, or what slope actually is. So slope is equal to rise over run. A lot of students can get to that, but what rise means is your change in y values, so up your y-axis or your vertical axis, and your run is your change in x values, so across your x-axis or your horizontal axis. So rise over run is what slope is equal to, and so what you do if you're calculating the slope of a line is you pick 2 points, call one of them point number 1 and one of them point number 2. It does not matter which you call point 1 or 2, but you need to be consistent with it. These two coordinates need to go with the same point, and these two coordinates need to go with the same point. You can't have y2 minus y1, x1 minus x2. That doesn't give you a valid reflection. You need to have the same points representing point 1 and point 2, or the same point representing those x and y values. So the following graph shows, for problems involving distance or displacement time graphs, speed is equal to distance over time. Now, as a science teacher, I have a problem with the fact that this graph is called distance versus time because you can't have negative distance. So maybe we'll call it displacement versus time, or maybe we'll just pretend that this is math class and I shouldn't be so picky. So what we have is I'm going to label these as 4 sections. So section 1, section 2, section 3, and section 4. And so it's distance in kilometers over time. So it looks like the time is about 65 minutes for this whole trip or something like that, okay? So just analyzing to start, over which time period is the skateboarder traveling the fastest? So what fast means is covering a lot of distance in a little bit of time. So it would actually be, you want kind of your steepest slope for the fastest. So steepest slope. And it looks like our section 4 would be our steepest slope. So it's covering the most amount of distance for the same amount of time. It's in total traveling 5 kilometers in 5 minutes, whereas everywhere else it's traveling 2 kilometers in 30 minutes. In section 3, it's in total traveling 3 kilometers in 20 minutes. So that section 4 is the steepest slope. So that's when they would be traveling the fastest. Over which time period is the skateboarder traveling the slowest? And so that would be the most gradual slope or a horizontal line. So what section 2 means is it's not changing speed. It's not changing its distance over time. So it's not changing distance. And so what that actually represents is it is stopped. Because it's not changing the amount of distance. It's at 2 kilometers at 30 minutes, and then it's at 2 kilometers at 40 minutes. So they took a little 10-minute break to hang out for a bit, and they didn't change their distance at all. So it was actually stopped. That's when they're traveling the slowest. They're not even moving, actually. And so what is occurring from 60 to 65 minutes? So that's section 4. So what's actually occurring? This one's kind of a weird question. So in section 4, basically what they're doing is traveling back to where they started from very quickly, because they go back to 0 in terms of displacement, we're going to call it. Moving back to where they started. And they're going fast. So you could calculate out the slope of each of those segments. Maybe I'll just do, just looking at section, let's do section 1 and section 3. So peeking at the graph, so actually calculating the slope. I just do want to practice that. So section 1. So I'm going to use this point and this point as my 2 points. And again, I'm going to erase this too, because that could get confusing. So for this first segment, it doesn't matter which point you call point 1 and point 2, just as long as you're consistent. So I'm going to call this point 1 and this point 2. So again, your slope is equal to y2 subtract y1 over x2 subtract x1. So my y coordinate of point 2 is 2. My y coordinate of point 1 is 0. My x coordinate of point 2 is equal to 30. My x coordinate of point 1 is equal to 0. So 2 subtract 0 is 2. 30 subtract 0 is 30. So if I divide that, I get 0.06 repeating, I think. And again, your rise is your y-axis, so that's kilometers, over your run is your x-axis, so that's 0.06 repeating kilometers per minute. That's the slope of that line, and it's also the speed that that skateboarder was traveling at that point. If we did section 2, we would find the slope was equal to 0 because it has no rise. So your y-coordinate at point 2 would be 2, and your y-coordinate at point 1 would also be 2. So you'd have 0 divided by 10, which is still 0. So just for any sake, section 3, can't quite see it. So again, I'm just going to erase the other stuff for now so I don't confuse myself. This was section 3, so I'm going to call this point 2 and this point 1. It doesn't matter as long as you're consistent. So point 2 is at 5 on the y-axis and 2 on the, or for point 1. And then on the x-axis for point 2, looks like it's at about 60. And for point 1, it looks like it's at 40. So that's 3 over 20, which if I punch that in, gets me 0.15. And again, that's kilometers per minute. because your rise is your change in your y value, which is distance. Your run is your change in your x value, which is time in minutes. So you could calculate out section 4 as well. You get a slope of negative 1 kilometer per minute. So the negative is just because it's moving in what we'll call the backwards direction. So you should get a negative value, that's okay. But it is what we would call faster because it's moving at a higher rate. Okay. I changed this in the other notes because I actually wanted to do part B before part A. So if you have the new updated ones, I think you should have this in a different order and spaced out a little bit better. Oh no, I haven't changed it in whatever. So we'll just do estimate the skier speed for the time intervals you identified in part A. Yours might say determine the skier speed in the 4 sections or something like that. That's okay. It has the same questions, they're just in a little bit of a different order. So again, we have kind of 4 discrete sections that we're going to call here. So we'll call this section 1, this section 2, this section 3, and this section 4. And maybe just give the video a pause and try calculating out the slope of each section. So in each section, call 1.1 and 1.2 and try calculating out the speed of each section. Then I can give it a go as well. So pause it and try. If you're coming back right now, we'll go over each of these. So section 1, we might have a little bit of different answers just if we estimated where the points actually were a little bit differently. So as long as you're relatively close, that's a-okay. So I said section 1 goes from about 1300 to 1200. Oops. And for that 1300, my x value is 0. And I thought it went about 11 seconds. You might have said 10 seconds, so your answer probably is pretty close. So I got negative 9.09. And again, that's in meters per second because your change in y is meters, your change in x is time. So section 2. So I used my 1200 that I had here as my starting point for section 2. And then I estimated that it went down to about 1075. I started with the 11 seconds that I had here, and I estimated that it went to about 27 seconds. And so for my speed, I got about negative 7.81 meters per second. So again, if you're off by a little bit, that's a-okay, just if you estimate it a little bit differently. For section 3, I'm not going to write it all out. I said it was between 1075 and 925, and the time was between 27 seconds and 35 seconds. So I got a speed of negative 18.75 meters per second. And section 4, I said it was between 925 meters and 800 meters at the end, and that went between 35 and 60 seconds, which got me negative 5 meters per second. So then I'm going to look up at that other question that was above, and it says, during which interval of time was the skier's speed the least? So we actually, in theory, could have answered that question first. So we would have said section 4. So even if we didn't do all the calculations down here, we probably could have given our best estimate that section 4, the speed was the least. Because the slope of the line, you can just kind of see by looking at it. It has the least steep slope. Was the lowest speed because it has the least steep slope. So it's covering the least amount of distance per unit time at that point. So that's calculating slope of lines. So we'll do one more, we're almost done. I like that this is numbered as number 2, whatever. So the gas consumption of a car on a 2-part trip is shown below. So it looks like Mario, because that's what it says in the graph, drove the first leg of the trip. Then he probably had to fill up his tank, get some Twizzlers for driving so much, and then go pee and then start leg 2. So that's what it means by leg 1 and leg 2. It's not the legs on your body. It's just talking about portions of a trip. So we have leg 1, which took 48 liters of gas, and he traveled 645 kilometers. And then leg 2 took 32.1 liters of gas, and he traveled 392 kilometers. It's quite the trip. So the first question, it says, during which leg does the car have better fuel consumption? So we assume he's in the same car. Maybe one of them he had to drive up hills a lot, so that's worse fuel consumption or something like that. So explain how you know. So just looking at this graph, we need to think what this means. So we have gas used as our y-axis. We have distance driven as our x-axis. So what I'm going to look at is kind of this point here. So right around 400 kilometers, or at 392 kilometers. We can compare those two graphs. What we see is leg 2 used more gas to travel the same distance. So looking at the red line on my screen, at least, the red line, it looks like they used 32.1 liters of gas to travel 392 kilometers, whereas on leg 1, they maybe used something like 28 liters. So in terms of car fuel efficiency, you want to use less gas to move the same distance. So we would say that the car had better fuel efficiency. So therefore, leg 1 had better fuel efficiency because it used less fuel to travel the same distance. So question B, it says, at what rate in liters per kilometer is the gas being consumed for each leg? So actually, when you're buying a car, they sometimes give you stats like this, either liters per kilometer or kilometers per liter. They actually kind of give you two very different pieces of information, and you want to think about which of them, but it's saying liters per kilometer in this case. So for leg 1, we want liters on top. So leg 1 took 48 liters to travel 645 kilometers. So 48 divided by 645 gets me 0.074419 liters per kilometer. And for leg 2, took 32.1 liters, and they traveled 392 kilometers. So that gives me a rate of 0.081888 liters per kilometer. And so thinking about what that information means. So we have two numbers, one higher and one lower number. So higher liters per kilometer is actually a bad thing because it's saying how many liters of gas does it take you to get a kilometer? So leg 2 has higher liters per kilometer, meaning it takes more gas to get the same distance. So that's what part C is saying. It says, does your answer in part B confirm your answer in part A? And yes, it does. And again, that's because leg 1 has a lower rate in question B, which means it takes fewer liters of gas to travel 1 kilometer. So you obviously don't need to add this in, but sometimes like car commercials, if you ever see them, will actually tell you kilometers per liter. So it's saying how many kilometers can you drive on 1 liter of gas? And in that case, you would actually want a higher number. You'd want to be able to travel more kilometers per liter. So just depending on how your rate is expressed, you need to think about what it actually means. So that's it. That's all for today. We'll do some more rate stuff tomorrow. It's definitely a related lesson. So I think you have some textbook questions. I will peek at that. I think you have some textbook questions to work on, and we'll see you for the next lesson. Bye.